chapter 4.2. We will be continuing with probability, but now we're going to look at and learn two probability rules. The first of these is called the multiplication rule. It's also known as the and statement because you're looking at probabilities with the word and. Now, what you need to realize here is more than one event is occurring. So the probability that event A and B are occurring. So in this case, that would be two events, and we want to know the probability and. So it's an and statement, so we know we're going to use the multiplication rule. And here's the formula that you would use. So the probability of event A and B would be calculated by first finding the probability of event A and multiplying that times the probability of event B given that A has already occurred. So here's an example. If you're going to roll a die 3 times, so we have more than one event occurring. Event 1 would be rolling it the first time, event 2 would be the second time, and event 3 would be the third time. So if we were asked to find the probability that we get a 3, and then a 6, and then a 2, if I write it in the formula, and it is an and statement, so we know you're going to use multiplication, this would be read, find the probability that you roll a 3, and then you'll multiply that times the probability that you roll a 6, given that you got a 3 on the first roll, times the probability that you roll a 2, given that you got a 3 on the first roll, and given that you got a 6 on the second roll. So what we would do is we would think back to what are the possible outcomes when you roll a die. That's 1, 2, 3, 4, 5, 6. So there's 6 possible outcomes. So when you roll the die the first time, what's the probability you get a 3? Well, there's 1 3 out of 6 sides. So assume, because we're going to, given that we got a 3, so assume you got a 3 on the first roll. So you pick it up a second time and you roll it. Now what is the probability you get a 6? Well, there's 1 6 and 6 sides to the coin. Or not coin, sorry, dice. So assume you got a 3. Assume you got a 6. So now you pick it up and you're going to roll it a third time. What's the probability you get a 2? Well, there's 1 2 6 sides. So we have 1 6 times 1 6 times 1 6. So when I multiply my numerators, I get 1. And 6 times 6 times 6 is 216. So I get 1 over 216. Now, that is definitely a number between 0 and 1, so I know I'm okay there. If I actually divided that, 1 divided by 216, you get 0.00462963. So it's way closer to 0 than it is to 1. So there's one example of using the multiplication rule. All right. Now what we're going to look at is we're going to draw 2 cards from a deck. So a deck of cards has 52 cards in it, and we're going to draw 2 cards. So we have 2 events. Event 1 is the first draw. Event 2 is the second draw. Now notice it says here, draw the first card, replace that card, and then draw a second card. And that word of replacement is going to be important here. All right, so we want to know what is the probability that I get a king on the first draw and a 3 on the second draw. So using the multiplication rule, that would be calculate the probability of getting a king, and you're going to multiply that times, assume you got a king, now what is the probability you get a 3? Now this of replacement is important. All right, so you're holding a deck of cards, you draw 1 card. What is the probability you get a king? Well, in a deck of cards, there are 4 kings out of 52 cards. So it'd be 4 over 52. Now, replace that card, put that card back in the deck, assume you got a king, but put it back in the deck. Now what's the probability when you draw a second time you get a 3? Well, there are 4 3s in the deck, and because you replace that card, there are still 52 cards in the deck. So you get 4 over 52 times 4 over 52. Now, you can multiply that. 4 times 4 is 16. 52 times 52 is 2,704. And what you'll find is when you reduce that fraction, you get 1 over 169. Now, if you converted that to a decimal, you would get 0.00591716. So it's a pretty long decimal, and you have to take it out several places because there's several zeros before you get a number. Now, this is talking about since you replaced the first card, then on the second draw you still had 52 cards. Now what I want to look at is still the drawing a king and a 3, but this time do not replace the card. So we still have the probability of a king times the probability of a 3 given a king. Okay, so on my first draw, what's the probability I get a king? Well, there's still 4 kings in the deck, 52 cards. Now, the difference in this one is, assume you drew a king and you will keep that king. You do not put it back in the deck of cards. So now when you go to draw your second card, what's the probability you get a 3? Well, there are 4 3s in there, but there are only 51 cards that you are drawing from. So it's 4 over 52 times 4 over 51. So because you did not replace, this number was affected because there was one less card. And this is 4 over 663, or 0.006033183. So I wanted to point out and show you the importance of when you replace or when you do not replace. Now, that leads us then into the discussion of when events are what we called independent events or dependent events. Now, independent events is when the occurrence of one event does not change the probability that the next event will occur. So, here is an example where we will roll a die. Well, I'm sorry. Independent events are when you roll a die, drawing cards without replacement. Now, here is an example that reads, roll a 4 on a die and flip a tail on a coin. Well, these are independent because you first are going to roll a die, and that has no effect then on how or the occurrence of when you flip a coin. So it is an and statement, so it's a multiplication. What is the probability event 1 is a 4 on the die and event 2 is tails on the coin? So the probability of getting a 4 on the die, there's 1 4, 6 possible outcomes, and we will multiply that times, assume I got the 4, but when I pick up the coin, what has occurred on the die has no effect, so the probability of getting tails is 1 tail, 2 sides to the coin. So I get 1/12. And then when you could convert that to a decimal if you wanted to, or you can just leave it as 1/12. Now, that's what we call independent, because what happened on the second event was not affected by what happened on the first event. Now, when they are affected, it's what we call dependent events, and this would be when there is not replacement to whether it be cards or any type of drawing that you do. So here we have an example. We have a bag that has 5 red marbles, 3 green, and 2 blue marbles. Now you're going to draw 2 marbles without replacement, and that's the key right there that makes them dependent. Find the probability of drawing a red and then a green. So we want to know what's the probability of getting a red marble and then a green marble. So it's the probability of red times the probability of green given red. So when I look over here at my bag, the probability of getting a red, there are 5 red out of a total of 10 marbles. So 5/10 or 1/2. Then we are to assume, because it's without replacement, so given that I got a red, so I want to assume I'm holding a red marble in my hand, and I'm going to draw a second time. Now what's the probability I get a green? Well, there are still 3 green marbles in there, but there are no longer 10 marbles in the bag. There are only 9. So this denominator was affected because we had without replacement. So we actually have 1/2 times 1/3 So we get 1/6 is our probability. And again, that's a number between 0 and 1, so I'm good. Now, that was the multiplication rule. Now we are going to look at the addition rule. Now, the word that you'll see here is or instead of and. Now, the other difference is there's only one event occurring. It says, what is the probability event A or B occurs? So they don't both occur, it's just one or the other. So it's an or statement. And this is addition, so it's the probability of A plus the probability of B minus the probability of A and B. So let's look at some examples here. So we're going to roll the die one time, one event, and I want to know that when I roll it one time, what is the probability that a 3 or a 6 is what shows up on my die? So when I place it in the formula, I have the probability of 3 plus the probability of 6 minus the probability of a 3 and a 6. All right, so when you roll the die one time, what's the probability you get a 3? There's 1 3, 6 sides. If you roll the die one time, what's the probability you get a 6? There's 1 6, 6 sides on the die. Minus, if you roll the die one time, what's the probability that a 3 and a 6 show up at the same time? Well, that cannot happen, so it is 0. So then I just add, so I get 2 6 or 1/3. All right, well, let's look at as far as drawing a card. Again, one event, you're going to draw one card. So when you draw one card, what's the probability you get a king or a 3? So it's the probability of a king plus the probability of a 3 minus the probability of getting a king and a 3. So when you draw one card, what's the probability you get a king? There are 4 kings, 52 cards. If you were to draw one card, what's the probability you get a 3? There are 4 3s, 52 cards. If you draw one card, what is the probability that you get a king and a 3 at the same time? Can't happen. So that would be 0. So you get 8 over 52, and that reduces to 2 over 13. So you're probably looking at it and going, well, what is the purpose of this? Because the two examples we did, that was always 0. Well, let me show you why you still have to consider that, because it will not always be 0. Here we have what is the probability of getting a king or hearts. So the probability of king plus the probability of hearts minus the probability of a king and a heart. All right, so in a deck of cards, if you were to draw one card, what's the probability you get king? Well, there are 4 kings, 52 cards. If you were to draw one card, what's the probability the card you draw would have a heart on it? Well, there are 13 cards with a heart on it out of 52 cards. Minus, well, if you were to draw one card, what is the probability that you would draw a king and a heart? Well, in a deck of cards, there is one card that has a king on it as well as hearts. So you have to take away that one card out of 52, because the king of hearts is included in this probability, the king of hearts is included in this probability. So you can't count the king of hearts twice, so you have to take one of them away. So we would have 4 plus 13 is 17 minus 1, so we would have 16 over 52. I believe, yeah, that is 4/13. Now, this brings up the terminology mutually exclusive. Mutually exclusive events are events that cannot occur together. Well, the king and the heart can occur together, so this is not mutually exclusive. But if we go back to the previous ones, a king and a 3 cannot occur together, So these are mutually exclusive because they cannot occur together, as well as getting a 3 and a 6 is mutually exclusive as well because they cannot occur at the same time. So if you'll notice, if your events are mutually exclusive, then this value will be 0. When they are not mutually exclusive, you will get a value other than 0. Then the last thing I want to look at with probabilities is probabilities that come from a chart. Now, this is actually in your book, and what it's talking about is if you were to go buy a car, if the salesperson was an aggressive salesperson or if they were passive, and whether a sale was made, so a car was sold, or no sale, meaning a car was not sold. So how this table works is there was a total of 1,160 customers. Of those 1,160, 580 times the aggressive sales pitch was used, 580 times the passive sales pitch was used. 686 times a car was sold, 474 times a car was not sold. And here in a minute I will explain these. Like this 270 means aggressive was used and they sold a car. Aggressive was used and they did not sell a car. Passive approach was used and they sold a car. Passive approach was not used and there was no sale. Or I'm sorry, passive was used and there was no sale. Sorry, I misspoke there. Okay, so this reads, what is the probability that the aggressive approach was used? Now, where you need to be careful here is aggressive just means any customer that was approached aggressively. So be careful, don't just use the 270. So aggressively, there was a total of 580 times that was used. So 580 over 1160, and that actually reduces to 1/2. So then the second one says, what is the probability that no sale was made? So here's no sale. There were a total of 474 customers out of 1160 that a car was not sold. So that reduces to, and it's such a big number, I just plug it into my calculator, and it's approximately 0.41. Use normal rounding rules and round to 2 decimal places. Now, C and D are what we call conditional probabilities. And here's where you have to be careful because a condition is being placed upon this. Here's the condition. We don't want to look at all the customers. We want to look at the customers where only a sale was made. Given a sale, so only a sale was made. So that tells me I am only looking at 686 customers. So always look at the condition and find that value, and that will be your denominator. So I'm only looking at this column right here. So how many of those were aggressive? There were 270 that were aggressive out of 686. And that is approximately 0.39. Now, D is the probability of no sale given passive. So now we're only looking at people where the passive approach was used. So I know my denominator will be the total of passive. So I come back to my table, I look at passive, that total is 580. So that will be my denominator. So I'm only looking at the passive approach and I want to find the no sale. So passive, no sale would be 164. So this would be 164 over 580, which is approximately 0.28. And you can reduce those fractions. I'm just kind of doing it the lazy man's way. Now, on E, you see that you have and, the probability of aggressive and sale. So if we fall back to our multiplication rule, that would be the probability of aggressive times the probability of a cell given aggressive. Okay, so the probability of aggressive, well, if you look back to question A, we answered that. That is 580 over 1160, or 1/2, but I want to show you in the full decimal. Then we have the probability of a cell given aggressive. Okay, so I have a condition, so I'm going to look at aggressive, and I know that's going to be my denominator. So here is aggressive, the denominator will be 580. So we want cell on aggressive, so here's aggressive, cell would be 270. Now, if you'll look at your fraction, I can cancel these two out and I get 270 over 1160. And that reduces to 0.23. And then the last one is an OR statement. So if we go back to, that means it's our addition. So the probability of aggressive plus the probability of cell minus the probability of aggressive and cell. That's my formula. So the probability of aggressive, again, we found that in part A. That was 580 over 1160. Probability of cell, so I have to go back to my table. Cell is 686. So 686 out of a total 1160 minus the probability of aggressive and cell. Well, we just found that in part E. That was 270 over 1160. So you would do 580 plus 686 minus 270, because we have common denominators, and you would get 996 over 1160, which is approximately 0.86. And so that's how you do probabilities from a table. And that is chapter 4.2.